Good evening, everyone. I hope you're having a good beginning to the weekend. I have been recording this for a while now. I've made so many mistakes. This is the 4th attempt. So hope this is successful. Alright, so this week in class we are going to learn how to calculate the ultimate strength of unidirectional lamina. It shouldn't be ultimate strength, it's ultimate strengths. How many strengths, you ask? There are 5. Why? Because a composite is not like your ordinary material. It's made up of 2 different materials and their properties are different in different directions. The whole lamina's property, I mean. So, in direction 1 along the fibers, you have 2 different strengths. Longitudinal tensile strength and longitudinal compressive strength. They are not equal. So, you have 2, and similarly perpendicular to the fibers in direction 2, you have 2 strengths, transverse tensile strength, transverse compressive strength. And of course, you have the in-plane shear strength. Maybe I should not draw this. This is 1, 2. Note here that we do not talk about out-of-plane load. It's more complicated. Okay. So in this pre-class video, you're just going to see experimentally how these values are obtained. Okay, so for first, this is the one we are going to do in class as well. Experimental longitudinal tensile strength. Alright, so here you have done so many tensile tests. I believe that you know this already, but because it is a composite, the standards are different. Here we follow the ASTM standard D3039. So it states that you have to use 6 to 80 degree plies that are 1/2 inch wide and 10 inches long. The specimen is mounted with strain gauges. You've seen extensometer before, so it's similar to that. It's mounted with strain gauges in the longitudinal and transverse directions because we want to record both. Tensile stresses are applied on the specimen at a rate of about 0.5 to 1 millimeter per minute, and 40 to 50 data points are obtained. And then using those data points, we draw graphs. This particular slide will be useful when we are doing our experiment. So you have to note something here. The standard even specifies the tab thickness. To make it look like a dog bone specimen, we need tabs. So you have the tab length, tab thickness, and even the tab angle. So we draw the stress strain graph, and from the linear portion we get the slope. That slope, if you remember anything at all, is Young's modulus, E1. And last week in class we learned the rule of mixtures. E1 equals EFVF plus EMVM, which is the V's are the volume fractions and the E's are the Young's modulus of the fiber and matrix. So from this graph, we also get the value of ultimate tensile strength and ultimate tensile failure strain also. When does a specimen fail? 1.56%. These values are for graphite, epoxy, unidirectional lamina. You can see actually the E value is pretty close to that of steel, for whom the value is 200 gigapascals. But you get a lot of weight savings, and that's what makes us do this very complicated job of manufacturing composites. So here there are 3 possible failure modes. Why do we study failure modes? Because it tells us what to look out for, it tells us how to design better, and just by observing the world around us, you get a lot of information. So here the failure mode depends on the fiber volume fraction. It does not have fibers like less than 40%, then you have brittle fracture, break. If you have this very common fiber volume fraction which we look for, which is between 40% and 65%, again you have brittle fracture of fibers, but there's pull out as well. What does pull out mean? This is what pull out means, not this one, just this second fiber. If you see, it is outside, or even the first 2. The first is just fiber fracture. Let me not draw, maybe that will make it better. So the first one you can see, this is just brittle fracture. But the second one you see is pull out, because you can see that the fiber broke and then got pulled out of the resin, so there's a void in the resin. So this is the most common type of failure mode. But if you have too much fiber, more than 65%, then the resin might not really seep into it, and there might not be uniform distribution. This is wrong. So what will happen in those cases is fiber matrix debonding. And that may also cause pullout. So here in the picture, actually you can see that there's kind of uneven breakage, right? That's also, that kind of shows you pullout and fiber fracture. And then we go to the second strength, longitudinal compressive strength, which means we apply compressive loads along the fiber direction. You have never done compressive tests, I think, but the METs have, and it is actually quite impressive to see, like how when you compress, the cross section actually bulges out, right? Why is this not disappearing? No. Why do I do this? Okay, so then compression. If along the fibers I compress my specimen, then there are 4 possible ways my specimen could get damaged or fail. So one is buckling. I hope you remember buckling. If you have long columns, length is very, very great than the cross section dimension, for example, then they might fail under compression or buckling. So here you can see that the fiber might buckle at the micro level, or it says transverse tensile failure here, which just means compression failure, or you might have buckling but also shearing that causes buckling. And then there's this shear failure mode where both fiber and matrix fail by shear. So these are 4 possible modes of failure. So here the ASTM standard we follow is, I believe, ASTM D3410. So it says we have to use 16 to 20 plies of 0 degree lamina that are 1/4 inch wide and 5 inches long. Why do we have short stubby specimens with a lot of plies? Is because we have seen the possibility of buckling happening, so we want to avoid that long length. And also, if the cross section starts bulging out, if it's too thin, that might not happen. It's not a good setup. That's why we want it to be thick to allow for the bulging of the specimen. So strain gauges as usual are mounted the longitudinal direction. Specimen is compressed at a given rate, and 40 to 50 data points are taken for stress and strain until the specimen fails. And then in typical fashion, you draw the stress versus strain diagram. Here you can actually see the compressive specimen setup. So again, it's the same process. You can get slope, which is the Young's modulus in the compressive direction, which is E1C for graphite epoxy as well. E1 compression is 199 gigapascals, which is pretty impressive, right? It's almost close to steel, very close to steel, equal to steel actually. And sigma 1C ultimate is, this is a lesser value than your tensile strength, as well as the strain is also less than your tensile strain, 0.995%. But while there, the strain was 1.56%, which means it could stretch a lot more than it can get compressed. Right? It is typical, this is expected, but the Young's modulus holds up pretty well. Then we come to the transverse tensile strength, the third strength, which is tensile strength, normal strength. So sigma, transverse, direction 2, and then tension. So how do we find this? It's the same standard you followed for transverse tensile strength. It's the same specimen, I believe. So the standard width of the specimen is 1 inch, 8 to 16 plies are used. And then, okay, this difference is mainly due to increase the amount of load required to break the specimen. Meaning, usually in the transverse direction, the properties are very, very low, right, compared to your longitudinal direction. So that's why you make it thick so that immediate failure doesn't happen. That's all. So 8 to 16 plies are used, but it follows the same torqued bone specimen. And then instead of using 0 degree, you use 90 degrees, I believe, right? Yeah. So instead of using 0 degree plies, now you're using 90 degree plies, which means instead of doing your lamina this way, this was the one direction, right? Now you're doing the same length, for example, but your fibers are this way and you're pulling at it. And then from there you do the same thing, same process, draw stress strain diagram, but now you can see the values that you get. In direction 1, the Young's modulus was 188 gigapascals. Direction 2, it's less than 10 gigapascals. Similarly, the stress and strain values are also very, very less. So you always try to make sure that you design something in composites and the load on it is mainly in the direction of the fibers. So here the transverse tensile strength prediction by just analysis and models without doing experiments is quite complicated. Why? Because it's not only about the fiber matrix. The bond strength plays a very important role. Are there voids? Are there residual stresses because of thermal expansion? There are a couple of factors that go into it. That is why predictive models or analysis of it becomes more complicated. But possible modes of failure are matrix tensile failure, understandable, it's direction 2, accompanied by fiber matrix debonding or fiber splitting. Meaning, what is fiber splitting? Because your specimen looks like this, right? So this fiber could split. And then we come to the fourth value, transverse compressive strength. Again, you have a particular standard to follow. Here, let me check if there's a standard given. It's the same standard 3410, but I believe the width is different, and in order to strengthen it, we use 30 to 40 plies. And similarly, here also analysis models are not satisfactory. It gets more complex. But that's why we prefer experimental analysis here. You use the same standard, same kind of compression test, but the specimen details are different. And then you record stress and strain, you draw the graphs, and then you get values. These are not so bad in terms of tension and compression. You get 93 gigapascals, which is not too bad. It's actually better in compression in the transverse direction. And then this is also for a graphite epoxy lamina. This 40 here just means 40 plies. Yeah. Sigma 2 C ultimate is 198 megapascals. This is very low. And the failure strain in the second direction when under compression is 2.7%. It actually behaves better in the transverse compressive case than the transverse tensile case. Matrix gives better protection in compression. So several modes of failure are possible. Again, the complexity goes up because of this, because of different modes of failure. Transverse matrix compressive failure, matrix shear failure with fiber matrix debonding, and fiber crushing. So many things, right? That is why doing an analytical model is difficult. Then the last one, in plane shear strength. Laminae plus or minus 45 just means plus 45, minus 45, plus 45, minus 45. The picture is more useful here. So then this type of fiber orientation is used and then it is pulled. Here what happens, there is of course the equation is given, shear stress ultimate equals sigma x ultimate divided by 2. Do you remember where this is coming from? I don't know if you remember this, but there's a section in solid mechanics where we talk about, oh yeah, if you apply shear, you have shear everywhere. But if your cross section is at an angle of 45 degrees, of course this is not 45 degrees, I am very bad at drawing. Okay, so 45 degrees, then actually you only have tension on the faces instead of compression. Your part will fail by tension even if shear force is applied. In that one, we actually will see that sigma is equal to 2 times tau. Right, so this comes from that. Here we do the opposite thing. We orient plus or minus 45 degree plies and then apply a normal stress, and from that calculate the maximum shear. And the shear strain is a combination of normal strains in both the x and y direction. You have these verticals to show that it is the absolute value, because if epsilon x is positive, epsilon y will be negative. We know that lateral strain, longitudinal strain. So that's why we are saying, okay, we are just looking at the numerical value to calculate shear strain. And then if you take the slope as usual, you get the shear modulus value. Here I think the shear modulus is for graphite epoxy lamina. You have 5.566 gigapascals, a low value of course. Tau 12 ultimate is 87.57 megapascals. That's not too bad in comparison with the transverse values. And the ultimate shear strain, failure strain, is actually good, 2.619%. It's even higher than the tensile strain, meaning if you have plus or minus 45 degree plies, it can stretch further than your normal 0 degree plies. Again, it's the same process, stress versus strain. Here also modeling analysis is difficult because you might have weak interfaces because of the angle, voids, Poisson's ratio. So everything is advanced mathematics, like elasticity, finite element methods, boundary element methods, finite difference methods. So all of your software use this finite element methods, but there are other things called boundary element and finite difference methods, which are all numerical methods, iterative methods. Take a long time if you do them by hand. That's why you have numerical tools to do it now. But again, why? Because we have a lot of differences in terms of fiber strength, bonding, spacing, diameter, and when you bring angle into it, automatically it gets complicated. The last part which I want to go over quickly is hygrothermal relationships. Hygrothermal meaning what happens when you have a temperature change, what happens when you have a humid environment. C here stands for moisture. If the moisture is being absorbed by the matrix mainly, what happens? So for a unidirectional lamina, this is the same relationship we have seen. Strain equals compliance matrix into stresses, correct? But here you add the strain caused by temperature change, expansion or contraction, and also the change caused by moisture absorption. So thermally induced strains epsilon T are equal to change in temperature multiplied by the coefficient of thermal expansion. I hope you've already heard of this. The coefficient of thermal expansion is defined as change in the linear dimension of a body per unit length per unit change of temperature. So that's why the unit is per change in per unit length per unit change of temperature. So meter per degree Celsius. How many meters is it changing? Every meter of the original body with every degree change in temperature. And similarly, you have moisture induced strains. So moisture induced strains, epsilon C, it's the same thing. The amount of moisture absorbed multiplied by, what is this called? The symbol, of course, you know, alpha and beta. Beta is just the moisture expansion coefficient. To be exact, linear coefficient of moisture expansion. So it is the change in linear dimension of a body again per unit length again, but here it's per unit change in weight of moisture content per unit weight of the body. So the unit is meter per meter per kg per kg. All right. So this is how the strains, the thermally induced strains and moisture induced strains are defined. So for unidirectional lamina, so now the strains already have two additional components. If you want to reverse it, we already know stresses are equal to Q matrix, which is a stiffness matrix, reduced stiffness matrix multiplied by the strains. Again, here you can see the strains have two additional components. Shear doesn't have, but the normal does have, because we are only talking about compression, tension. In terms of moisture absorption, again, your linear dimensions change, right? So we're not talking about the shear at all here. So then if you bring angular lamina, it gets more complicated, because we know global strains are equal to transformed compliance matrix S bar multiplied by your global stresses. So again, here you have two additional components, thermally induced and moisture induced strains, but they're also in the global dimensions. So how do you get them? Thermally induced strains again is temperature change multiplied by your alphas, coefficient of thermal expansion. And then your moisture induced strains are amount of moisture absorbed multiplied by your betas, which is coefficients of moisture expansion. But these are also in the global directions. So again, how to convert global to local is, this you already know, is using the transformation matrix, which is a combination of sines and cosines. It's the same for alpha and beta. You can even see the divided by 2 that is there for the last value. If you have an angular lamina, because of the angle itself, it's no longer just x and y, you have xy, which is shear. But in the local direction, it's still 0, but you might have a value in the xy direction. So how do we experimentally get this? For thermal expansion, of course, you mount strain gauges on the specimen. Let me see if there is a particular standard specified in your book. No, the standard is not given. But you measure the dimensional changes, and that is why you have two strain gauges. The test specimen is made of a 50 by 50 or 2 inches by 2 inches, 2 inches by 2 inch specimen, and 8 plies unidirectional composite. And then 2 strain gauges are placed perpendicular to each other. So you can see one is in the 0 degree and one is in the 90 degree. And then it's put in an oven. The temperature is slowly increased. The strain is measured by the strain gauges. And then graphs are plotted. On the right hand side, you can see the graphs for alpha 1 and alpha 2. Because it's a composite, of course, the coefficients of thermal expansion, meaning how much your composite expands, is also dependent on the direction in which you're measuring. That's why we are using the 2 strain gauges. So you get alpha 1 and alpha 2, which are of course functions of fiber volume fraction, Young's moduli, and in the second direction, Poisson's ratio. So this is what you draw. You measure the strains and you draw graph strain versus temperature. So for a graphite epoxy lamina, alpha 1 and alpha 2 are given here. You can see alpha 1 is very less, alpha 2 is even lesser. This is why carbon fiber composites or graphite epoxy composites are preferred to be used in space applications, because their expansion, the coefficients are very, very less, meaning they don't expand or contract as much with temperature variation. Similarly, you have moisture expansion. Here what happens is the fibers or the specimen is made and it's placed in water, and moisture expansion strain is again measured using strain gauges in 2 directions. So that's how you get beta 1 and beta 2. You can see actually in your book the graphs are not given, but it's the same process as temperature change, only this time we are recording the weight that the specimen incurs and then strains, of course. So from there, using the graphs, using empirical models, elastic models, you get this very complicated looking equations for beta 1 and beta 2, where the moisture absorbed by fibers, moisture absorbed by matrix, the densities, the fiber volume fractions, Poisson's ratio in the second direction, everything matters. But mostly because the fibers are well coated by the resin, we say that the fiber does not absorb moisture. So in that case, with this very complicated equation becomes very small, because this whole term becomes 0, and then this whole term becomes 0 because the fiber doesn't get any moisture, so the weight changes nothing. And then here this term becomes 0 because del CF is 0. Del CF, this term becomes 0. So you have a lot of simplification going on. So beta 1 reduces to a ratio of Young's modulus of matrix over E1, density of composite in matrix, and moisture absorbed by the matrix. And then beta 2 again reduces to a more simpler formula. And then if we say, okay, we use a high EF to EM ratio, meaning the fiber is very, 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 very stiff compared to the matrix, so the matrix is very weak material, then this is almost 0, this ratio is almost 0. So then beta 1 becomes 0. If you apply that to beta 2, you're left with a very small number. Okay, so you need not memorize any of this. Of course, all your quizzes are open book quizzes, but this is a very important part that we have not discussed yet. With that, we are finished. Hope you have a good weekend. Restful weekend. Please sleep well, please eat well, please rest well. I will see you at 9:45 on Monday. Bye-bye.